Today we are going to discuss the two Maxwell's equation. We will drive these Maxwell equations. First of all, our first Maxwell equation is del dot E is equal to rho upon epsilon naught, where E is representing the electric field and rho is representing the charge density. This is the charge density per unit volume, that is Q upon V. Epsilon naught is our permittivity constant, and this symbol is representing the divergence of electric field. We know that according to the definition of electric flux, that is E dot ds is given by Q upon epsilon naught from the Gauss law equation, and the charge with the help of this equation can be written in the form of density and volume. Now we will put charge in the terms of density and volume. If the volume is very small, we can write it like this: the charge density into small volume, and integrating with respect to volume we will get the total charge. We will substitute this value of charge in above equation, and we will get rho dV integrating divided by epsilon naught. It will give us the electric flux, and according to the divergence theorem we can give the relation between the electric flux and the divergence. We know that the electric flux is given by the divergence of electric field integrating with respect to volume. Hence, by using our divergence theorem, we can substitute E dot ds in the form of divergence. Hence, we have del dot E dV is equal to rho dV divided by epsilon naught if we use this term in the above equation, and if we cross multiply these two terms we will get del dot epsilon naught E dV is equal to rho dV. On equating both sides, we will have del dot epsilon naught E is equal to rho, or we can say that del dot E is equal to rho upon epsilon naught. Also, we can use the displacement current D is equal to epsilon naught times of electric field in the previous equation, and we will have del dot D, that is the displacement current vector, is equal to rho. Hence we obtained the first Maxwell equation with the help of using the Gauss law. Next, we are discussing our fourth Maxwell equation, that is del cross B is equal to mu naught times of current density plus rate of change of displacement vector with respect to time. This is our displacement current. Whether first we discuss this equation, previously we will first just find out what is our displacement current. Let us consider the case of capacitor, and in case of capacitor we know that capacitor blocks DC and it allows AC to flow through it. Let us consider we have given an AC supply to this capacitor, and we know that when positive half of the wave comes to the capacitor, let us consider this plate becomes positively charged and this become same in opposite nature negatively charged. We know that when negative half of the supply comes, this plate becomes negatively charged and this plate becomes positively charged with time. And when this plate is positively charged and this is negative, we know that there is an electric field increasing with time as the signal is becoming more positive. And when there is a change in electric field, the changing electric field is responsible to produce the changing magnetic field. Hence, in this case, this magnetic induction is depending upon current as well as depending upon the displacement current. In this wire, there is conventional current, and this current density J is given as current per unit area. This J is taken with the help of this conducting wire, and this D is taken from this electric field which is producing a magnetic field, and again this changing magnetic field will produce a changing electric field, and hence we obtain a type of displacement current in between these two parallel plates. Hence, this J is due to this conducting wire, and this D is due to the gap in between the positive and negative plates. According to Ampere's circuital law, we know that the line integral of magnetic field is given by mu naught times of the current. As we know that we have to convert this current into our current density, we can take I as surface integral of our current density. Now, substituting this equation in the above one, we will have B dot dl is equal to mu naught times of J dot ds. But according to Stokes' law, we can convert B dot dl in the terms of del cross B. Hence, we are substituting this B dot dl in terms of del cross B, that is B dot dl can be written as del cross B dot with ds. With the help of Stokes' law, we can convert line integral into surface integral. By using the Stokes' law in the above equation, we will have del cross B dot ds is equal to mu naught times of J dot ds, and on equating these both sides of the equation, as we are saying, we will have del cross B is equal to mu naught J. We know that now we are saying that we have del cross B is equal to mu naught J. The first term of the equation is obtained. Now, what about the second term? If we take divergence of any curl of a vector, we know that always that term will equal to 0. Hence, del cross B, divergence of del cross B is equal to 0, implies that del dot mu naught J should also be equal to 0. If del dot mu naught J is equal to 0, it means that J, that is according to the continuity equation, we will have change of charge density with respect to time that should be equal to 0. It means charge density remains constant, and if charge density remains constant, it means there is no change in charge with respect to volume, or we can say that if we have a conducting material, then there is no sinkage of the charge and there is no source of the charge. If there is sinkage of charge, then rate of change of charge density will be negative, and if there is a source of charge within this element, then the rate of change of charge density that should come out to be positive. Hence, from this conclusion that charge density is equal to 0, because from equation of continuity del dot j is equal to minus rate of change of charge density, and hence if del dot j is equal to 0, as we know that mu naught is a constant, divergence is operating only upon the current density, and if this is equal to 0, it implies that the current density gives the result that the charge density is also 0. But in every case this is not possible, this is not always works like that, that the charge density is equal to 0. Let us consider the charge density is not equal to 0, and to proceed that, let us again, we have a assumption that del cross B, which is taken as mu naught j according to Ampere's law, is also having a term with this mu naught j, that is mu naught j dash. Now if this term is equal to 0, even then del cross B gives us some output, that is mu naught j dash. Now we will find out what is mu naught j dash. Now again, if we now operate the divergence, we will have del dot del cross B is equal to mu naught del dot j plus mu naught del dot j dash, and as we know that curl of any divergence is always equal to 0, from this result we will have del dot j is equal to negative of del dot j dash, where del dot j is representing the current density, and we will have del dot j dash is equal to minus of rate of change of charge density is equal to minus del dot j dash. Hence we find out that del dot j dash comes out to be rate of change of charge density with respect to time period. And according to our previous equation, we know that del dot E is equal to rho upon epsilon naught, and from this the charge density rho is equal to epsilon naught times of del dot E, and hence we find out that using this equation, in the above equation del dot j dash comes out to be rate of change of epsilon naught times of del dot E with respect to time period. Or we can also say that putting displacement d current vector is equal to epsilon naught times of E, we will have rate of change of divergence of displacement vector with respect to time, that is del dot j dash comes out to be like this. And if we compare both equation, we will find out that del dot j is nothing else than rate of change of displacement current vector with respect to time. Substituting this equation in our assumptions, we will have del cross B is equal to mu naught j plus mu naught rate of change of current displacement vector with respect to time, and if we take mu naught as constant or common from these two terms, we will have mu naught times j, that is our current density, and this is our rate of change of displacement current with respect to time, and hence we will find out that del cross B is equal to mu naught times of J plus rate of change of our displacement current with respect to time period.